In today's lesson, we are going to talk about stretch and compression of transformed functions. In the previous lessons, we said that the general formula for the transformation of a function, if assuming that the base function is f of x, is going to be another function g of x with the following parameters: a times f, b x minus h plus k. In the previous lessons, we talked about first the reflection about the x and y axis, which is determined by the sign of a and b coefficients. We said that if a is positive, nothing is going to happen to the base function. If a is negative, then the base function is going to be reflected about the x-axis. For b, we said that if b is positive, nothing is going to happen to the base function, but if b is negative, then the base function is going to be reflected about the y-axis. Then we talked about the translation, which is determined by the parameters h and k. We said that if k is positive, the function is translated or moved up or down along the y-axis. If h is positive, the base function is going to move to the right, and if h is negative, then the base function is going to move to the left along the x-axis. Today we are going to talk about the stretch and compression of a function. The stretch and compression about the y-axis is concerned with parameter a. We are going to say that if absolute value of a, the reason we say absolute value is that if a is positive or negative, the rules stays the same. If you take the absolute value of a number, you are going to throw away the sign and you are going to deal only with the number without the sign. For instance, absolute value of negative 5 is 5. The absolute value of 10 is 10. Now, if the absolute value of a is greater than 1, then we are going to stretch about y-axis. If absolute value of a is between 1 and 0, then we are going to compress about the y-axis. So a works for only y-axis. For b, we are going to look at b again with absolute value. We are going to say if absolute value of b is greater than 1, then we are going to compress. We are not going to stretch anymore. We are going to compress about x-axis. But the tricky part comes here about by how much, by what factor. The factor that we are going to compress about what x-axis is 1 over absolute value of b. Here, the stretch and compression about the y-axis was by a factor of absolute value of a. You are going to stretch by a value which is equal to absolute value of a. You are going to compress about the y-axis by a value, absolute value of a. But when we go about x-axis, the compression and stretch is going to be 1 over absolute value of b. When absolute value of b is between 1 and 0, then we are going to stretch. We are not going to compress. We are going to stretch about x-axis by a value equal to 1 over absolute value of b. So these are all about stretch and compression of any functions. Now we are going to do a couple of examples to see how this works in actual problems. In the first example, we have the function f of x is equal to square root of x. We are supposed to write the equation for g of x and h of x, where g of x is 2x and h of x is half f of x, and describe the transformation. Then transform the graph of f of x to sketch graphs of g of x and h of x and state the domain and range of each function. First of all, we know that f of x is square root of x, which is the base function for radical function. Now, g of x is going to be 2 square root of x, because it's 2f of x, and h of x is going to be half square root of x. Now we are going to talk about the transformation. You can see that g of x, since a here is 2, which is greater than 1, we are going to say that the graph of f of x is going to be stretched along the y-axis by a factor of 2. For h of x, because a is 1 over 2 and it's between 1 and 0, we say that the graph of square root of x is compressed by a factor of half or 0.5 along the y-axis. Now we are going to sketch each graph. The table of value for f of x is going to be x, y. We are going to pick the point 0, 1, and 4 for x. If x is 0, then square root of 0 is 0. If x is 1, square root of 1 is 1. If x is 4, the square root of 4 is 2. So we are going to get 1, 2, 3, 4, 1, 2, 3, 4. If x is 0, y is 0. If x is 1, y is 1. If x is 4, y is 2, which is going to be somewhere around here. So this is going to be our f of x. Now let's look at g of x. G of x, the table of value for the same x's is going to be, if x is 0, 2 square root of 0 is 0. If x is 1, 2 square root of 1 is 2. If x is 4, 2 square root of 4 is 2 times 2 is going to be 4. So we get the same point here. If x is 1, y is 2. If x is 4, y is 4. So we get something like this one. You can easily see that the graph of the function g is the same as graph of function f, but it's going to be stretched along the y-axis by how much? By factor of 2. For h of x, we are going to have the following table of values, the same x's. If x is 0, we get half square root of 0 is 0. If x is 1, half square root of 1 is half, which is 0.5. If x is 4, half square root of 4 is going to be 1. So if x is 0, we get the same point 0. If x is 1, it's half, so it's going to be somewhere around here. And if x is 4, then y is 1. Then we get a graph like this one, which is obviously a compression of graph of f by a factor of 0.5. Now the question is that what is the domain and range of each function? You can see that the domain for each function, all of them, the domain is x in R, and x has to be greater than or equal to 0 because all the x's to the right of the origin are acceptable, and the range is going to be y in R, and y has to be greater than or equal to 0 for all of them, since all the y's over or above the origin are acceptable here. The next question is f of x is the same, meaning f of x is square root of x. We have to find g of x, which is f of 2x. So we say that g of x, which is f of 2x, is the same as, remember, f of x is square root of x. So wherever you see x, replace it with 2x. So it becomes square root of 2x. And h of x is going to be square root of half of x. Now, what we have to do is first explain the transformation here. Since here you multiply, your b value is 2 in g of x, the b value is 2, and the absolute value of 2 is greater than 1, then we know that g of x is a compression of f of x along the x-axis by a factor of 1 over 2. H of x, since b is 1 over 2, and absolute value of 1 over 2 is 1 over 2 is between 0 and 1, then we know that h of x is a compression of f of x along a stretch of f of x along the x-axis by a factor of 1 over 1 over 2, which is going to give you 2. Now to graph these again, we are going to find the table of values here. So again, I'm going to pick x as 0, 1, 4. When x is 0, f of x, which is square root of 0, is 0. When x is 1, square root of 1 is 1. When x is 4, square root of 4 is 2. So this is the table of value for f of x. Now I'm going to find the table of values for the same x's, but this time for g of x, which is equal to square root of 2x. Now when x is 0, 2 times 0 is 0, square root of 0 is 0. When x is 1, then it's going to be square root of 2, which is about 1.4. When x is 4, then we are going to get square root of 8. Now we are going to do for h of x, which is square root of 1 over 2 times x. The same value, x is 0, 1, 4. If x is 0, 1 over 2 times 0 is 0, square root of 0 is 0, so it's going to be 0 for y. If x is 1, it's going to be square root of half. And if x is 4, then we get square root of 2. Now we are going to try to plot the function. So we are going to sign 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. For f of x, when x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 2. So we get a point here. So this is going to be my f of x. Now for g of x, when x is 0, y is 0, so again this point. When x is 1, y this time is 1.4, so it's going to be somewhere around here. And when x is 4, y is square root of 8, which is going to be about 2.8. So if x is 4, y is 2.8, which is going to be about here. So this is going to be my g of x. And you can see that g of x is stretched, is compressed along the x-axis. Or in another word, we can say that it's stretched along the y-axis. So this is your function f here, and you are compressing about the y-axis. That's why you're getting g of x. For h of x, again we have x0, y0, which is this point. Then when x is 1, y is square root of 1 over 2, square root of 0.5 is about 0.7. So when x is 1 is about 0.7, which is about this point. And when x is 4, y is 1.4, square root of 2. So it's going to be somewhere around here. So the function, the graph looks like this one. So this is going to be your h of x. And as you can see, this is going to be a stretch along the x-axis. Now, the question now is the domain and range. You can see that the domain of each function is x in real number, and x has to be greater than or equal to 0. Everything to the right is acceptable, and also everything over the origin is also acceptable. So the range is going to be y in R, and y has to be greater than or equal to 0. In the next example, we are given a function g of x. We are supposed to find the base function, describe the transformation, and then sketch the graph. The first one, g of x, is equal to 3x. It is easy to see that the base function is f of x is a linear function which is equal to x. Now, compared to the base function, we can see that g of x is, since a is 3 and it's greater than 1, we can say that this is a stretch of a factor of 3 along the y-axis. So the graph looks like this is y is equal to x, which is f of x, and y equal to 3x is going to be something like this line. So this is g of x. The next example is g of x is 4x squared. The base function f of x here is going to be a quadratic function, which is x squared. And since a again is 4 here, then we can say that the base function is stretched because 4 is greater than 1 along the y-axis. So roughly, if this is f of x, which gives g squared, if you take these two branches and then stretch it upward, you get something like this one for g of x. In this example, we have a mass which is attached to the end of a spring. We define the period as the amount of time that it takes for the mass to move from its starting position. Let's say the mass is here and this is your spring. The period is the time that it takes for the mass to start from here, go up, and then down, and then back to here again. This is called the period of the function. And the period is given by this formula. T is equal to 2 pi square root of m over k. M is the mass of the object, which is this guy, and k is the spring constant. Depending on the type of the string, k is determined by the material that the spring is made up of. Now we have a company which needs to show how different springs they perform compared to the other ones. The following table of value is given. The first part of a problem says graph the period versus the mass for various spring constants. If basic is K value is 100, strong is 200, and heavy duty is 300. Just remember that the function T is equal to 2 pi over m over k. So for T basic, T of B, the function is m over 100. For T strong, this function is 2 pi over a square root of m over 200, which I can write it as 2 pi square root of 1 over 100 m over 100 times 1 over 2 under the square root, which is the same as 2 pi square root of 1 over 2 m over 100. For T of heavy duty, this is 2 pi over m over 300, which I can write as 2 pi square root of 1 over 3 m over 100. Now the reason I wrote it as m over 100 because I want to compare the graph of basic with strong and heavy duty. Now I'm going to roughly graph these functions. In fact, x in our case is m and y in our case is period t. Now for t, because we're dealing with 1/100th of a number and we know how the square root function looks like, if t of b it looks like this one, if this is t of b, if I graph this function, then if you look at t of s, which is this function, you can see that the base function is going to be, if we assume the base function is the period for basic spring type, then it's square root of half of that one because of half. Since b value is half here, then we say that the graph of t sub b, which is the basic, is going to be stretched by a factor of 2. If you stretch this graph by a factor of 2, we get something like this one along the x-axis. So this is going to be t of s. Now for t of heavy duty, you can see that the b coefficient is 1 over 3, so it's going to be again stretched along the x-axis by a factor of 3 now. So it's going to be something like this one. Now this tells you something interesting, is that for any period, if we draw a horizontal line, you can see that if this point, which represents this mass, for strong spring, you can see that to have that period, you can have this much mass, and for heavy duty, to have the same period, we need this mass. So for heavy duty, stronger mass is going to produce the same period compared to a basic or strong spring. Now the last part of the question says, how are the graphs of strong, heavy, and basic springs relate to the graph of the basic one? Uh, if you if we again redraw the basic graph, the strong one and the heavy duty, you can see that the strong one is a stretch of the basic one by a factor of 2, and the heavy duty is a stretch of basic one by a factor of 3.